Right, ladies, today we are going to look at the next section in geometrical optics, and that is Snell's law. So if I look at the guidelines, Snell's law is described as the ratio of the sine of the angle of incidence in one medium to the sine of the angle of refraction in the other medium. And then the formula for Snell's law, we've got three versions of it. So it says n1 sine theta 1 is equal to n2 sine theta 2. And what you have to remember here is n is the refractive index of the material in which the incident ray is found, and sine theta 1 is the sine of the angle of incidence. And this is equal to n2 sine theta 2. So n2 is the refractive index of the material that has the refracted ray, and sine theta 2 is the sine of the angle of refraction. It can also be written like this, and then it can also be written, and I think this is the one I'm going to use because this is what it looks like on the data sheet. So n sine theta 1 or sine theta, so what have we got? We've got the refractive index of the material that contains the incident ray. Sine theta is going to be the sine of the angle of incidence, which is equal to nr, which is the refractive index of the material that contains the refracted ray, and sine theta is then sine of the angle of refraction. I think the easiest way to explain this is by making use of an example. So the example that I would like to use is the worked example on page 111. So they say that light travels obliquely from glass to water, and this just means that the light strikes the boundary at an angle, but not 90 degrees. So I've done a little illustration here. They do ask you to do that as well. So what is happening here? Light is traveling from glass to water. So if it strikes the surface at 90 degrees, we said that it actually then, although the speed is affected, direction isn't, and it would just go right through, and it would basically travel along the normal. But it strikes at an angle, so there's my incident ray. I've drawn in the normal. I've got my angle of incidence between the normal and the incident ray. Now it's going from glass to water. And if I look up the refractive index of the different substances in my table, I see that glass has a refractive index of 1,52 and water 1,33. So I know that glass is more dense than water. Of course, we knew that, but if it was two substances that we didn't really know that much about, we could just look at the refractive index to see which one's more dense and which one's optically less dense. So because light is traveling from more dense to less dense, I know that it's going to speed up, and I know that it is going to be refracted away from the normal. So that means my angle of refraction over here between the normal and the refracted ray must be greater than my angle of incidence over there between the incident ray and the normal. Then we get to the actual, so this we already did before, but now we get to the actual calculation using Snell's law. They tell us that the angle of refraction is 20 degrees and we have to calculate the angle of incidence. So I've written down my formula. N is the refractive index of the material that contains the incident ray, so that means it's glass, so that's where I get the 1,52 from. Sine theta 1 sine theta, is the angle of incidence, and that is what I'm trying to work out, so I don't know what that is. Then the refractive index of the material that contains the refracted ray, which in this case is water, and that's 1,33, so that's where I got that from. And then sine of the angle of refraction, and the angle of refraction was given as 20, so sine 20 degrees. So that means I just now need to get theta alone. So firstly, sine theta, if I divide by 1,52 on this side, I must do the same on that side, and I get sine theta is equal to 1,33 times sine 20 degrees divided by 1,52, and the angle then works out to 17,41 degrees. So what do I use Snell's law for? I'm working with 4 quantities here. So I've got 2 refractive indexes and I've got 2 angles. So 3 bits of information will be given, and then the 4th you'll have to calculate whatever that might be. And then lastly, according to your guidelines, you must also be able to calculate or determine the refractive index of an optical medium when light travels from a vacuum or air into that medium. The formula that we then use looks like this. Refractive index is equal to sine theta 1 divided by sine theta 2. Remember, this is the previous formula that we had for refractive index. We said it was equal to C divided by V, where C was the speed of light through a vacuum, 3 times 10 to the power of 8, and V was the speed of light through that medium. So this is just a different method that we can use to calculate the refractive index. So sine theta 1 is always going to be your angle of incidence, and that is always going to be the angle in either air or vacuum. Theta 2 is always going to be your angle of refraction, and that is always going to be the angle in the medium of which you are trying to find the refractive index. So again, I've just got an example here. I've got light traveling from air, refractive index 1, into an unknown substance, and I want to calculate the refractive index of this unknown substance. The angle of incidence is given as 35 degrees. The angle of refraction is given as 22 degrees. So refractive index is equal to sine theta 1 divided by sine theta 2. So theta 1, always the angle of incidence given as 35 degrees. Theta 2, always the angle of refraction given as 22 degrees. And that gives me a refractive index of 1,53. I can now go back to my table and I can look up the refractive index to try and identify the unknown substance. In this case, glass is given as 1,52 in the table, so this is close enough. So that means this unknown substance that I've got here would probably have been glass. Right, and then I am going to ask you to go look on page 111 at exercise 5.3 and on page 113 at exercise 5.4, and if you can please get that done by Monday, and on Monday we'll take a look at the answers for that. Thank you, ladies.